Je boš bolj stal.
During the snow, it's really hot in the aquarium. Sorry?
The winter garden.
Winter garden, just winter.
Zweite.
Yeah, really.
Такие ga moram noto nesti. Vse, da ne bojo pil sam. Kaj pa sam?
Zemlje.
Ja, ne delam.
Ampak ne delam, ne večem.
Ja.
Imaš mogoče tipinga, IP-ja.
Je, zdaj ga vzrgam. Hotel sem iti na hotspot, zato da je zadeva...
Pa se imaš... Dobro, kako doks. Ne zmerjaš.
Razum?
A ja, razum, ok.
No, jaz sem zapisal v skriptih, da sem se lepo naredil
Ja,
lokalno, ja. Da dobro se treba zaglavati s tem žitjem.
a nimaš ti onega umestnika za kabel? Ja, piše povezano. Da, ok, dobro ne umestnik.
Šti Bora predstava, kaj je tvoje?
Ja, da sem zdaj preseneten.
Ja, to je težka naloga. Je samo slajde, moraš deliti vse ostalo.
Ja, je.
Ja, zadnji blok.
Ja,
Trenutno pa...
A da je še kamera se ugasen. Ti si.
Stop video.
Ja.
Ja, sem ga začel. Ne si razloga za res.
Ja, kar prek te gledajo.
Ja, vse ga vidijo, tudi kjer to je postavljeno. Ja.
Da ga vidiš skupaj.
Lepšo se.
3D reproducira.
Kaj? Ja, ne spasi?
Je lahko kdo 3D reproducira.
Jaz sem bil na internetu. Neki igralci. Oni za njih pravijo, da res 3D model včasih igrajo v filmih igralci.
Ja.
In pa v bistvu vlečejo malce. Namesto da bi skrenili, ali kaj dan danes. Želimo oblačil vam malce. Znam ne, zakaj bi stavili njihove modele. Njihove modele.
Pa še nije to vam zdiga.
Jaz sem razumel, da je. Da je ni problem.
Če ga oblečeš malce, da ti skeniraš.
Itak, ja, ti ga pa ti obleč, pa pač razviješ in malce kak, ne, in pa je da razviješ.
Ja, če ta talun, kakor si naredil,
Ja.
da pa ti se skeniraš, če tukaj bolj dolgo traja. Ne vem, to mogoče.
Po drugi strani pa verjetno težji del pod skeniranje je verjetno 3D printer, če je pa da ste delo dejansko. Kako bo zdaj ga pa?
Moja prilažje zrošili ustvariti 3D model na miški, kako še dotajajo.
Ja,
narejanje za film.
recimo, pa ne kaj ne dobijajo zares, nekaj masa prerozbov. Pa sem nekaj preprosto. Paramet. A ja.
Ta črta,
Ja.
logo ti pa ne vidiš.
Ja.
Ni centriran logo na črto.
Seveda, mi pač na desni več.
Ja, ne, je pa svoka, ker ne moreš res videti, sam srednje črte, ker jaz smo to že rekel.
Ja, ne, ta asimetrija ne bi ja.
Ne, pa ne ta asimetrija, pa moram biti v srednjo slajda, srednjo črto.
Ja. Vprašanje pa bo zdelo.
Pa smo dobili te logote v kakšnem vektorskem formatu, ali
Mislim, da si da.
takem, da se ga da tudi prebrati.
Ja.
Z enega sem najdel, ko mi ne odpre.
Mislim, da je SVG.
A ja, da obstaja SVG.
Neko mapo se da dobiti
Nek zadaj sem iskal, pa
Če tam pa da odpreškamo vsemo, pismo, vse. Že en dolg PDF, malo
na strani od faksa je file, kjer so noter PNG-ji, pa nek vektorski format, ki ga nastane tukaj.
Sure.
Torej obstaja še nekaj drugega.
Stare aqui no todo estou, porque nós não trouxemos, nós não pista que eu faço, nós não trouxemos primeira, nós não temos que fazer como olha, como outros, né? Três, não, chipa.
Posso dar teu ritmo pronto.
Já tem o tipo de monte de considerar que isso é de shirt, não. Mas vai haver tipo de shirts. So guys, would you prefer to have the logo centered like it is now, right? So the content, the full content is centered, or the middle line is centered?
Full content.
Yeah, okay.
I think you can have both if you move mathematics into a separate line.
Yeah, sure.
Yeah, but then the vertical axis are insane.
I can change the size.
I was thinking it's more impossible, it's a long one.
You can also make university data in 3 lines.
Yeah. These decisions.
Thinking the best way to see you just try. Yeah, the thing is, it's hard to center the middle line.
What have you seen now?
Yeah, I mean, I can try.
Let's try to do it.
I'm just saying it's,
You could just put the like logo at the bottom right.
I'm just saying it's hard to center it on the.
You want to send
The
it?
center it on body out like this.
Yeah, how do I do that?
Usually.
Yeah,
So it looks good.
At least we got professional logos. The very first time we started doing this, the result was literally appalling. It's like worse than if you told AI to do it. It was literally like a student project, not even a good one.
Or you can cancel it on, you know. So.
Or not, if they're not allowed, that's the solution. This is the official logo and it needs to be as this. No. Ah, fuck, it was a master site.
Ooh.
So, okay, how did I say?
The break the whole presentation.
Yeah, because it goes to the front. Okay, then. Forget it because it's already 15 past anyways, so we should,
Oh yeah, the clock.
we should start. Yes.
I think on the website you have .ai files, so you can open them in Illustrator.
Yes, we have it.
Yeah, if you can open it with this page, sure.
My Inkscape completed.
It's a good idea.
Yeah, not reaching out to get illustrated.
Yeah. On the show notes.
Yeah.
So welcome to this week's ASTRODEBATA. It's my great pleasure to introduce today Bori Jamnik, our new PhD student. So I was Bori Jamnik's advisor on the master thesis, which he successfully completed his master defense in September this year. And now he's continuing as a PhD student in our group under the supervision of Tomasz and myself. And today he's going to talk about the continuation of the project that we started or we did for the master thesis. It's called Binary Stars, as you see for the title. And we hope to, yes, refine this, further improve it, and then publish some good results. And I will let Bob talk more about this. But we also did other projects during studies, so we're very happy with it. What Bob is doing is very proficient at handling large data sets and the analysis of those. And we talk more about this today. So please, Bob.
So, thank you, Gregor. So, as Gregor mentioned, this was the mostly as a part of my master's thesis. And my presentation will mostly focus on what I did during my master's thesis. So, to just can make a short overview over what I'll be talking about today. I'll start with some binary star properties in general. Then we'll look at more specifically at the classical observational methods with which we try to detect or measure properties of binary systems. We will then move on to how unresolved binary stars impact color absolute magnitude diagram. And then we'll see what the model of our galaxy is, and then of course what the results and what our future prospects look like. So binary stars, okay, so here's some text missing, but okay, so yes, so binary stars are very interesting. In fact, most of the stars in our galaxy exist in binary or higher order multiple stellar systems. The highest order of stellar multiplicity that's confirmed is a system of 9 stars that are gravitationally bound. Of those, binary stars are the most common. And because they are so common, they're important in star formation studies or modeling, in determining properties of exoplanets because they could impose some biases, or in studies of supernova type 1A, which are standard candles, and understanding binary systems that lead to this supernova type 1A are, of course, very important in gravitational wave research and so on. Now, of course, if you want to determine the properties of binary star population, we need to be one of the easiest ways, perhaps, is to measure parameters of some individual systems and then make a statistics on these parameters. Now, we usually measure properties of binary systems using these methods. So depending on the method which you can detect or measure properties of a system, we then group binary stars into different groups. So we have astrometric binaries, where we actually observe the movement of stars in the system. So movement of stars on the sky, which is a consequence of the movement of stars in a system. If we can resolve both stars, so we see 2 dots in the sky, we say that these are resolved astrometric binaries. If we can't resolve, we can maybe see the movement of the photocenter of stars, which is of course the unresolved binaries. So perhaps one fun fact: this GIF is a GIF of star Alpha. It's the so-called the demon star, and it's the demon star because it's a binary star. And every, I think it's about 3 days, one of the stars crosses in front of the other, which makes the primary star lose about 2 magnitudes of luminosity. And in the old times, it was thought that this is some kind of demonic effect. Then these stars that cross in front of each other are, of course, eclipsing binaries in which we trace or infer the properties of the system based on eclipses of the system. And then the spectroscopic binaries in which we study the shifts, Doppler shifts of spectral lines due to movement in the system. Now, again, another fun fact. So the Doppler shift itself was developed by Doppler because he tried to explain why stars have different colors. He thought that all of the stars are naturally yellowish white, and stars moving in binary systems are the reason why we have stars of different colors in the sky. And that's why he developed his theory of Doppler shift, which I thought was pretty fun, actually. Of course, there's one problem, or there are, I guess, 2 problems. One is that all of these methods have pretty impactful or are plagued by pretty impactful selection effects. Meaning you can only probe a part of binary star population. For eclipsing binaries, we are very limited by the inclination of the system. For astrometric binaries, we are very limited by the fact that we need to spatially resolve stars in the sky. So stars need to be far apart. And then there's the other thing that all of these, so all the methods are relatively time consuming in the sense that you need to probe a pretty large part of stellar orbit in order to determine some parameters of this orbit. Of course, for example, if we turn back to astrometric binaries, if we need stars that are far apart, but then again have short orbits, we are really limited only to the closest stars. And all of this together leads to studies that are limited in either volume or the samples are frankly incomplete. So the idea, just actually Gregor's idea, was can we use large astrophotometric databases of perhaps Gaia or Pumas to think or to infer something about these binary star population parameters. Now, we tried to make use of the fact that if we have a binary star that is unresolved, so we observe both stars as a single source, these stars can reach places on the color absolute magnitude diagram that are otherwise unreachable by single stars. What we mean by that, if we add star of the same mass. So in this study, we thought that, we said that all of these stars are born at the same time, meaning they are the same age, meaning they are the same ethnicity. So if they are also the same mass, we're saying, yeah, the stars are it's basically the same stellar properties. So if we put two equal stars together, we will get stars that are way too bright for their color, based on the absolute. If we put together primary, so a more massive star with a less massive star, we will see a smaller rise in luminosity, of course, but the color of the stars will be a bit more on the redder side. And so this is this graph that I thought is pretty, so it depicts this effect pretty nicely. We can see an isochrone, so this is for solar stars of solar ethnicity and solar age, for different masses, of course. And then we can see how adding a star with a mass ratio of Q affects the movement of a binary star on the color absolute magnitude diagram. So deep blue is a single star, and then we are adding companions, more massive and more massive companions up until deep red, which is two equal mass stars in our source. Now, our idea then was, let's create a synthetic galaxy of single, so non-binary stars, and then we add a population of binary stars based on some prescription. Then we would compare the color absolute magnitude diagrams of our synthetic galaxy and observational data, and in this way try to find parameters of binary star population that would best fit the observational data. Now, if we just look at the synthetic galaxy for a start, we can very nicely see what actually happens when we add a population of binary stars to a population of single stars. So we can see that the main sequence, so above the main sequence, we get another, so binary stars, and also we can see that the diagram as a whole gets a bit broader. So this upper part, so this part above the main sequence, this is what we are actually trying to probe. Now, for some technical details, our galaxy of single stars is based on Galaxy O, which is then in turn based on Besançon galactic one. We didn't actually use the code, but we rewrote it a bit, wrote it in Python, and updated it with some other prescriptions, some from the original author Sharma, and some were just our own, just so the single star galaxy a bit better fit our data. We modeled halo, thick, and thin disk, so we didn't model bulge. This was because in the end we were only probing the first 2 kiloparsecs away from the sun, so we do not think that there are many bulge stars which we are observing. And then we of course had our binary stars. So we model our binary star population based on 6 free parameters. The first is the binary fraction for sunless stars. The second is the change, or the rate of change of binary fraction with primary mass, which we model as a linear function with slope k massa. Then we also model the change of binary fraction with system metallicity, again as a linear function with k math. We use log normal period distribution for all of the stars in our sample, which again we use both the mean and the standard deviation of this log normal distribution as our free parameters. And then we also model our mass ratio distribution. We model this as a power law with power q power. So these 6 are our free parameters. Then we also randomly orientate and position, so randomly orientate our orbits and randomly position our stars in these orbits. Now, to fit, we use an MC, MC method called ABC. It's a bit different from the general MCNC method, since that it's approximate. So, in short, what it does, we select random input parameters, we use these parameters to generate data, and then this is the part that is different from the MCNC version, is that we compare this generated to observational data using the distance measure. If distance is sufficiently small, we accept our parameters, otherwise we try again. So because we are allowing some distance sufficiently small, so what does this actually mean? This means that this epsilon is not 0. If this epsilon was 0, this would be approximate Bayesian computation, because we'd be sampling directly from the posterior. But because we allow some occurrences of this non-zero distance, we also allow we get some bias on our posterior of parameters. Now, we need to do this because, as it turned out, if we try the normal MCMC with Poissonian likelihood, the convergences are just way too slow. Whereas in this case, we were managed to get some decently converged results in some reasonable amount of time. Now, perhaps some of you, or I assume that some of you at least, have noticed that we were missing another parameter when we were determining our orbital parameters. This is eccentricity. At first, we were trying to also model the eccentricity distribution, but we soon saw that at the resolution that we are assuming, the Gaia's resolution that we are assuming, the eccentricity actually plays no role. So eccentricity distribution plays no role. We also tried modeling then so this is again modeled as a power law, our eccentricity distribution, as we can see whether it's just a flat distribution or power law of phi. We can almost see almost no differences except from some stochastic effects. So we also tried then to just model all orbits circular, because that's just computationally much easier, but then it turns out that modeling eccentricity itself is important, but the distribution of eccentricity is not important, and resolution we assume. If the resolution was 2 orders of magnitude better, then this parameter would be very important, but here it's not. So of course, we proceeded to validate our map. So at first, instead of observational data, we used synthetic galaxy as our observational data, meaning we created a galaxy with no parameters, and then fit our synthetic galaxy and try to recover these same parameters. With this, we know that we are using exactly the correct model, and we're just seeing whether there are some degeneracies or perhaps biases that are inherent to the method and to the color absolute magnitude diagram of perhaps Gaia color bands. So the resulting fit is actually very promising. We recover all of these true values in between our uncertainty that we model between 16th and 84th percentile. And if we compare these perhaps to some uncertainties that are typical to observationally, so to some studies that are based on classical observational methods, for example, we can see that the uncertainties are at least as good as those of classical studies. And then in some cases, for example, that's for our log normal distribution, these are usually just like, yeah, it looks like a log normal distribution with mean something and sigma something without any uncertainties. It's just like, yeah, this looks like it could be okay. So in some cases, we can even add some uncertainty where usually there's no uncertainty even model. Of course, this was the ideal case with no observational errors and no randoming that would impact our data. So next step was, of course, to still use synthetic true galaxy instead of observational data, but then simulate randoming and observation random. So extinction we model with biased 3D dust maps. This unfortunately means that we need to discard all of the stars that are lower than minus 30 degrees declination. And we can, of course, immediately see that the recover or the best fit is not as good as it was. Still, qualitatively, they still seem the same. But then if we take the ratio, so this is the ratio of best fit to truth galaxy, this should be, or in the ideal, in the perfect fit should be all the same color. We can see a lot more of discrepancies, but still we still attribute most of all of these to some stochastic processes in our method. So the resulting fit are still good in a sense that we recover all of the true values within our uncertainties, but the distributions are much wider. If we then compare this back to the ideal case on the same scale, we can see that in our ideal case, the uncertainties are much narrower and our inferred parameter refers to a much greater degree of accuracy. So still we thought, okay, it's still something, we can still obviously, or it looks like we can still infer our parameters. Let's see what happens if we use real data. So for data, we use the third data release of ESA's Gaia mission. And here, maybe for just an illustration why we are wanting to use this astrophotometric data. In Gaia data release 3, we have about 3 orders of magnitude more astrophotometric data than we do have spectrometric data. So this is an illustration why, how expensive are these classical methods themselves. And then we need to add on our selection effects there. So if this could work, this would be really nice. In the end, we used about 800,000 stars within 2 kiloparsecs. And also we made sure that we are at least 10% away from the galactic plane. So we wanted to have less problems with extinction, reddening. We also wanted our relative uncertainty of parallax to be under 10%. And maybe I'll talk about this number also a bit later. Now for our results. First, we needed to have two new parameters. And these are the ratios of number of stars in each component. So until now, we knew what the correct ratio was, or what the ratio was. Now we don't, so we need two new parameters. And at first, this was our first try, so just these two new parameters. This is actually a pretty, still qualitatively a pretty good fit, but we can see that we are missing, looks like our ranking is a bit underestimated. So our next three parameters that we had was global reddening scaling factor, which was basically just, yeah, we've got this much reddening, multiply reddening across the whole galaxy by a factor alpha. So this is what happens then. On the right hand side, we do have some, it looks like the coverage is better, but then look at the ratio of that speed of the ratio. It seems as if now the reddening is overestimated. And actually this alpha was even then a bit suspiciously high, something about 2.7. So our feed told us that our general dust estimation is too low by a factor of 3, which is a bit big of an underestimation. So then we tried to correct this by adding two more parameters, which were offsets on x and y axis. Of course, there are some problems with these two parameters, since you don't really know what's going on. You don't really know what you're trying to, what's the physical thing that you're trying to fit. There could be some biases that you could fit maybe. So if the whole Gaia dataset was under or overestimated in color or luminosity by some amount, again, this seems a bit unlikely. Also, these two parameters are, of course, correlated with the dust scaling factor, because they move our galaxy in the same diagonal axis. But still, like the resulting quantum fit looks pretty nice now. Unfortunately, the problem is that before we use these two parameters, our fractional binary stars for solar-like stars, primary stars, looked something like this. So what our method was telling us was that pretty much all of solar-like stars in our galaxy were binary, which we know is not true. We expect values like from 40 to 60%, let's say. And then we use these two parameters, and things changed. Unfortunately, now they change into the other extreme. So this was another problem. Still, we're not really satisfied with these results. So we thought, okay, now if we go back, we can see that on this ratio plot, we've got some problems, okay, in the top left, which I will touch on a bit later, but also here on the bottom right. So we say, okay, let's use a smaller area of the color absolute magnitude diagram and see what happens there. So now this actually looks pretty promising. Again, we have some problems on the blue giant part color absolute magnitude diagram, which we will again touch on this a bit later. But otherwise, things are pretty nice. And also the resulting fit is much, let's say, we're not that bothered by it anymore. The binary fraction for solar-like stars now ends somewhere expected level. so this is perhaps an example of a good fit parameter. Then we also have some parameters that are, the fits are not that nice, in the sense that our distributions are very wide. But still, all of these parameters are inside our, let's say, they do agree with the return. That is all that is K mass. So what our fit is trying to tell us is that the more massive the star, less probable it is that the star is binary. This is one of the things that we actually know pretty well, and it's exactly the other way around. The more massive the star, the more likely it is that it's in a binary system. But this was a parameter that no matter what we did, we also introduced some new parameters, for example, because these blue giants are most likely young stars, we tried to force our galaxies to have less young stars. We changed the single stars street, no matter what we did. This scale factor for our for changing of the binary fraction with primary mass star was, yeah, it's stayed negative, and we could not or still cannot fix this. Now, of course, this is quite problematic. So we thought of a few things that could be done. First is, of course, this is a very simple one. The only thing that we're actually scaling with differing primary star is the binary fraction rate. Then if we maybe look at what actually use the period distribution that we try to model with the single log normal distribution, we can see that the distribution itself is very dependent on the type of star. So we can see maybe on the mass of star. So modeling all of this with a single period distribution, so a single log normal distribution, of course, looking now, maybe seems a bit naive even. So it's not really expected that we could find a single log normal distribution that would fit all of this. Furthermore, even when we do model our scaling with mass and atomicity, we use the simplest possible function. So it's the linear function. Now, if we may look at what our data is saying, is that this is so the change of multiplicity fraction, but qualitatively it's the same as change of binary fraction. So we can see that it's, so just make sure that you're aware that this is a log axis on the x. So modeling all of this with a simple linear function also seems to be over ambitious, especially considering the fact that our that it can change quite dramatically. In the sense that you can't really go much under one solar mass star, but the most massive stars can also reach a few 10 solar masses. So it's not really even a symmetric distribution of masses that you're working with. So this is of course a problem. And for example, there's a paper of Andrei Bercha and his student, I think his student was the first author actually, Mark was, which models the primary mass as a function of, I think it's kind of Copernicus. So this is for some kind of similar function will probably work better with this. Also another idea of how to deal with this, let's say, too simple distribution is to use some non-parametric fitting to fit these distributions with histogram bins instead of some analytical functions. So this is what we are working on. This is what I hope to have some intermediate results, at least today, but then there were some problems with our computing cluster and unfortunately I don't. Then of course there are some possible problems with our singles galaxy. Also in some other literature we can see that the business on the electric model has some problems with these young stars, so with our blue giants. So this is, I think, also need to take into account. Then, of course, are we adding binaries into our singles galaxy in our own way? Meaning, we have some single galaxy model that's based on some measured mass distributions in our galaxy. Then we're just adding stars into these measured distributions. So there are, of course, some problems that could arise from here. Now, an idea how to deal with this would be that instead of randomly assigning stars, we could take the stars from our galaxy and take the stars together to make binary systems in which we wouldn't change our mass density function that dramatically. So this is maybe an idea on how to do this. Also, we did not take any binary evolution into account, meaning that any stars that are close enough to one star will influence the evolution of the other star, which could also then, of course, influence the photometric properties of this star. Would we are also using all of this physics. And then, of course, the question is, are we actually modeling our reddening and observational errors correctly or adequately? Perhaps an idea would be, of course, not to model reddening, but rather to take some use the reddening of stars in our Gaia survey, and then try to redden our observational sample instead of simulating our extinction. We did try this, but just briefly. So just doing this did not solve anything. Perhaps fine-tuning can do this would solve some things. Also, with observational errors, of course, it is, well, we could just take a better sample or a better measured sample with less uncertainties on our data. The problem is that we're not really sure if the fact that the star is a binary influences or how much it influences the uncertainties of our, especially astrometric measurements. So this is the parallax error dependent, or is it much higher, or at which relative parallax error do we see the effects of binary stars in our sample? So this is, of course, also a thing that you need to take into account. Then again, the question is, how do you actually model which star will be observed as a one and which star will be observed as two sources? Now, yeah, in some kind of a general telescope, you say, yeah, the resolution of the telescope is so and so, but with Gaia, you're observing the same star in different phases, in different orientation of the satellite itself. So the question is, what's actually going on there? So these are our known problems or known deficiencies of our model. So of course, what can we do next? Improve our model, that's pretty obvious. We also mentioned some ideas on how to do that. Take data in other passbands, so combine this color absolute diagram with color absolute diagrams in other passbands that could perhaps uncover some other properties of our binary stars. Then one of the problems of this is that each fit or each attempt takes about 8,000 CPU hours to converge. Meaning we could use some faster methods. An idea was to use some gradient descent algorithms. We could try more things and perhaps get to our conclusions faster. Then, of course, there are the option of imposing stricter constraints on data, but as I mentioned, we need to be careful with that. We need to think about that. Like a few days ago, there was just a study published in Archive that deals exactly with how the binary stars influence the parallax measurements in Gaia or something like that. And then, of course, if we fix all of this, the next logical step is to add in higher order multiples, so triples and so on, and also from these populations. So yes, that's it from my side. So thank you very much.
So, thank you very much, Mark. Do you have any questions? Yeah, let's go ahead.
I have one question and one comment. One comment is that on the can you go back a few slides where we have the comparison plotted?
Which one?
Keep going.
This?
Yeah, here, like
Yeah.
BP minus RP of let's say 1.5.
Yes.
The theoretical isochrones are way off there. It can be you can have errors of like half a magnitude just in theoretical isochrones. So that's pretty much comparable to the difference in magnitude you get for your binaries. So I suppose you shouldn't worry too much about that part.
Okay. So this was also the reason why we went from this area of our color magnetic diagram to this, but I wasn't aware, honestly, that also at this part of the parametric magnetic diagrams that the isochrones are also so off.
You say we should get cut even more.
I'm not sure what the best course of action is,
Yeah.
but you should at least be aware that
Okay,
isochrones can be
Yeah.
quite far off.
Okay.
It depends also on the composition of the stars.
Yeah.
It gets complicated, but they can be like half a magnitude off
Okay.
in some cases.
Okay. Thank you. That.
That's a good thing.
Yes. Thank you.
And then my question is, when can we expect this improved Galaxia model to be public? So Galaxia right now only has single stars in it. You said you improved it by adding binary stars into the
I think
models.
there are some prescriptions on how to add binary stars into Galaxia model. I think one of the updates of Galaxia also included some binary star model, if I'm not mistaken.
Well, it includes a bit of work. You have to do it yourself, right? It'd be really nice to have the Galaxia model where you say, okay, produce me a synthetic survey with these parameters, and you already get binary stars out of that.
Okay.
It may be some parameter that controls the resolution of your survey. So
Yeah.
to join the stars into a single source, you have to.
Yeah,
This would be a highly cited paper if you're able to produce a code that does that.
so we are the first ones using a galactic model, including binaries, and there have been other works where they do this, but they do it for different purposes, right? They want to figure out something else on the galaxy. So those codes, I guess some of them are public and exist, also based on the galaxy. So
I don't know of a single code that would do this well, or at least in a
okay.
practically usable way.
Not sure about that, but sure people can build.
I know many people do this, but
Yeah.
sometimes you need a code that in a few lines you get your synthetic survey.
Yeah, the fast.
Without going through the whole physics of binary stars.
Yes, isn't the fast BGM to the fast business galactic model such a code?
But that's just a galactic model. That's not a synthetic survey.
Okay. I see. Yeah. Not sure, something to look into it. Because, yeah, when publishing such a code, we say yes, indeed. So.
To some degree, in my view, this is also kind of unknown, because you're speaking most about mesostars. The binary functions are weak, but this is just telling you it is binary, not which parameters. And so, in a way, I mean, it's a kind of back and forth. I mean,
That's why I'm saying you need a code that produces a synthetic survey, because when you compare observations to your models, you're limited by some resolution. When you see a point source on the sky, which might be a binary. So it doesn't help you if you get all the parameters. You still have to calculate how many of those you're going to resolve and how many you want, and what's going to be the effective radial velocity you're going to measure, and so on.
Yeah. Okay. More work to do?
Yeah.
I mean, these are the things that I think we can control. The resolution and the orbital parameters. The thing is, this is a very simple model, right? So it's just these linear scales, or not even, or some of these distributions, most of these distributions are not even scaled with regard to mass or velocity of primary star. Also, if we say, okay, yeah, but, you know, adding a new distribution on how to model some parameters is pretty easy. Again, the problematic part, I think, the most problematic part in our method is, are we actually imposing any biases on mass distribution with the way that we are adding our binaries or our secondaries into the system? So I think this is probably the best thing, or the most important thing one needs to sort. One needs to at least have some pretty good physical arguments why you're doing it the way that you are doing it. Also, I'm not that familiar with the Saison fund itself, so I'm not sure what, to what account, if any, is there this, the existence of binary stars even count, like are they, account for this extra mass that would come in the shape of binaries, are they accounting for that in their galactic model? I'm not sure about that. If you, so.
Yeah, I mean, a lot of these models they just come out of the basic model, which was the business on at the time, and but they do these things differently in the way that they
Yeah.
it. But if we were to construct a general code that does all this and all those things that you mentioned now, like the input parameters, right?
Yeah.
That would be a code very useful. But that doesn't do a lot of work.
Maybe another choice is, you mentioned several times the kiloparsec, okay, as a unit.
Yeah.
Now this looks like close, I mean, warm water to the distance to the center of the galaxy, but actually it's far away because Gaia is strongly biased to 2 kiloparsec. I mean, so somehow you have a kind of fair measurement of pretty much everything up to maybe 80 parsec or 100. Of course, this is skewed your numbers and you can have this kind of problems, but still maybe just test in a kind of, let's say, smaller samples whether you have some strong biases. That would be maybe the way to go, right?
Yeah.
I mean, even further reduce.
Yeah.
Yeah.
And maybe, you know, corrective plan can have your problems with programming elsewhere in the class and so on.
That's what we do about it.
Yeah, we don't have the memories for that. I mean, yeah, it's just like, I guess the thing we actually wanted to do was the first part, which is the more method validation, so just synthetic to synthetic. And in this case, you avoid all these problems with, are you actually modeling your galaxy correctly? Just to see, like, is comparing this CAM is even a viable option in some kind of term. And I think we showed that, but of course, going on to the real data, there's a lot of work still to be done.
Yes. Questions?
Yeah, maybe you talk about stochastic plugins. Did you try changing the number of stars maybe to observe this?
Sure, I think I've got a slide. So the problem with this is that, of course, the more stars you take in, the longer computation. So I'm not saying that there is no problem with the fact that our galaxy is not infinitely large, but I do not think that this is our main problem at this point. Maybe I will have some. Yeah. So yeah, maybe this. So this is the, let's say, relative Poissonian noise per beam that you expect. You see that this main part of our let's say binary stars, or the main sequence, we will expect Poissonian errors of the order of like 10%, which again, it's not negligible necessarily, but it's also not so large that we necessarily be worried about it. So yeah, so what we do here is just we get generated this galaxy 100 times with different random seeds. Then we just, well, yeah, it's the mean number of stars. So it's the standard deviation of number of stars in a bin divided by the mean number of stars in the bin. So again, we also, this is supposed to be done as an illustration of why those areas in our ideal case are noisy. It's really the Poissonian noise that's contributing to this, but it also can serve as a, well, just as a way to see that, yeah, most likely isn't the Poissonian noise that's causing our problems.
Of course, this was done to see what the epsilon, the ABC, that should be on.
Oh, yeah.
What's the epsilon there?
Yeah, what's the epsilon that's still like how high can the epsilon be, our distance metric, so that we're not trying to search for good random seeds instead of good binary star population parameters.
Yeah, this was actually my second question, how did you determine the epsilon?
Yeah, it was.
Yeah, so this is, I mean, it's not perhaps theoretically or mathematically the sound wave, but I think that if we set like epsilon to 450 here, we know that we shouldn't go below 450, otherwise we're really just wasting time searching for good random generator seeds.
Anything online?
No,
Yeah, just
it's already 5 past 12. That's the clock. It's wrong.
It's fine, Astro.
Yeah.
Okay. Good. So I just want to make one more one, maybe. So Paul mentioned that, of course, we're looking for the primary signal of the binary population is the secondary main sequence, right? That is the strongest feature of data type. But of course, binary population does change the shape across the data. Right? Also on the, especially on the clusters and also on the giant branch, although less visible, right? Okay, so I think we should end that up today. Thanks everyone for being here. Do we already have a date the next Astrodebata?
No, nothing is scheduled.
Then you will be notified by the usual channels. Okay, let's thank God again.